Okay, today I will tell you about cylinders, flexibility, and quadrics. This talk is based on joint work with Hoang Le Truong, which is going to be hopefully published soon. Otherwise, I'm going to be executed. So the setup is, as usual, nothing fancy. The ground field is algebraically closed of characteristic 0. Varieties are irreducible, so by default when I say a variety, I mean an irreducible variety. So the magic spell to cast here is integral separated scheme of finite typology. And when I talk about algebraic group actions, I mean regular actions, so that this map is a morphism, and GA, as usual, is the one-dimensional unipotent group. Okay, the first section is cylinders and GA actions. So I assume that everyone remembers what is a GA action and the correspondence with LNDs on the algebra of regular function for an affine variety. So the main definition of this talk is the following. Let X be a variety, arbitrary variety. For the definition it doesn't matter, affine or not. A cylinder in X by a cylinder in X, I mean an open subset U together with an isomorphism. U is, well, a cylinder with A1 fibers, A1 times Z for some affine Z. Well, let me draw the picture just in case. So that's your cylinders. That's the Z. And the fibers here are all A1s. Okay. And also yet another definition. Let me say that an action alpha of the group GA on a variety X, I say that this action is cylindrical if there is an isomorphism once again. X is a cylinder and alpha acts by translations along this factor. Along A1. So, of course, when you have a variety of this form, you can always form an action of GA just simply by translating each fiber. Okay, I think this is clear. Well, note. Here I also want Z to be affine. So note. In this case, X is of course automatically affine. And what's the orbits of this action? Well, it is clear that the orbits are just those fibers. And orbits are just A1 fibers. So there's this construction which connects cylinders with GA actions. So let me tell you about this here. So let X be affine. And this construction is from the article Kishimoto, Prokhorov, and Zeidenberg. 11, I think. So what it does, given a cylinder, we can construct an GA action. So if we have a cylinder, we can always produce a GA action with the following properties. So there exists a GA action, alpha on X, such that, well, let me say that the complement of this cylinder are fixed points, and alpha, the cylinder is automatically then an invariant subset. So if I restrict alpha to the subset, I will get a cylindrical action, like here. Is cylindrical. Wait, no. Just too quick. Not yet, just. And alpha just has fibers, has orbits equal to A1 fibers, has orbits equal to A1 fibers. Okay, so if you have a cylinder, you can always produce an action such that outside of this cylinders, those are just fixed points, and here everything moves along the fibers. Yes, yes, thank you, that's important. A principal cylinder. What I mean by principal, that's an open subset, so a principal open subset is the non-zero locus of some regular function, right? And conversely, if I have an GA action, effective GA action, then I can also find a cylinder. Then I have a principal cylinder, principal U, principal cylinder. U, such that alpha restricted to U is cylindrical. Yes, the complement doesn't have to be fixed points. We'll give an example a bit later. So, how do you look at this? That's some sort of invitation to people who in algebraic geometry don't like the algebraic part, so don't like those LNDs. That's some pure geometric criterion. So if you like only the geometry part in algebraic geometry, that's the invitation for you to study GA actions. Purely geometric criterion. And what's dissatisfying about this thing is that here I have orbits just A1 fibers, and here I have cylindrical action. So here it does not necessarily act by translations. But this can be this obstacle. There's a simple remedy for this obstacle, so claim. If I have a cylindrical action, if I have an action on a cylinder, such that orbits are A1 fibers, then automatically alpha is cylindrical. But here are some quirks to this. that may be not the same isomorphism, because we can move along fibers with different speeds, but I can choose another isomorphism to make all the speeds the same. So that's it's going to be just the translations. Okay, so we can then give another definition and say that let U be a cylinder in an whatever variety, and we say that an action of GA on X is induced by this cylinder, is induced by U if this holds with together with this claim, this holds. So if alpha restricted to U is cylindrical and the complement are all fixed points, and X without U are fixed points. So we can sum up. Instead of this, we can write this as principal cylinder induces an action, induced action. Okay. Principal. So cylinder is an open subset, right? So a principal open subset is the non-zero locus of some regular function. That's all. Okay. Is it understandable so far? So
lost a little bit about these points in the complement.
yes.
They, as you said, cannot be fixed.
So if you have a cylinder, you can always produce an action such that the complement is fixed. But if you have an action and you found a cylinder, then the complement may not be fixed. Okay? They may have some...
because it is done by a bigger cylinder. Okay.
Well, I don't know about this. We'll talk about this in a moment. So the rest of this section is kind of independent from the rest of my talk, but nonetheless, I want to say about this because in my opinion, those are some neat stuff going on here. Okay. So the question that arises naturally is, so if you look, you have here principal cylinders. So those are defined by some functions. And what are those functions? What do they correspond to? Well, I have an answer for this, but I need to introduce another definition, or maybe recall a definition. So it's purely algebraic, so let A be an affine K-domain. So read as the algebra of regular function on an affine variety. And D is a locally nilpotent derivation on A. The plinth ideal is so plinth of this derivation, plinth ideal is just the intersection of the kernel with the image of this derivation. Yes. Why is it an ideal? It's not an ideal in A, but it's an ideal in the kernel. The kernel is an algebra, so it's an ideal in the kernel. And another claim. So once again, X affine. We fix a GA action. D is the LND corresponding to this action of K of X corresponds to alpha. And I fix a function h. Okay, that's the data. Then I have this criterion. So the principal open subset U, I denote principal open subsets like this, d sub x of h. So that's the non-zero locus of h. So that's h non-zero. So it's a cylinder. Corresponding to alpha, so I mean that alpha restricted to the cylinder has fibers, has orbits A1 fibers corresponding to alpha, if and only if h to the power, to some natural power is in Plinth ideal for some k natural. Okay, and one direction is just actually the construction from this paper. So given an action, they find an element in the Plinth ideal and then they construct a cylinder. But the converse is also not so difficult. But then I have from this a corollary. So what's the geometric meaning of this Plinth ideal? So corollary. So once again, I want to have this x alpha d as before, as above. And let us just take all the cylinders such that they correspond to alpha and put them into one collection. So Uy, just all principal cylinders. All principal cylinders corresponding to alpha. Then the zero locus of this Plinth ideal, well, it follows from this claim that it's just the complement to this union of all those cylinders. Right, so everything that you cannot cover by a cylinder is given by Plinth ideal.
Plinth ideal is the ideal in the kernel.
Yes. Well, whatever, we can generate an ideal here.
So
and
this is not Plinth ideal, this is ideal generated by Plinth ideal.
Yeah, because I've seen this notation not for ideals, but for arbitrary subsets. So you can just generate an ideal, of course, and then also radicalize them, okay? Yeah, and this doesn't matter because you end up with a radical anyway. So that's some pretty stuff. Personally, I think that's interesting, but it's once again independent of the rest of my talk. So let me give an example / question. So for A3, I can have an action like this. So it corresponds to the LMD. I move x to y, and then y to z, and then z to 0. So the action is as follows: x plus sy plus 1 over 2 s squared z, then y plus sz, then z. And the orbits are parabolas of the form x equals 1 over 2z y squared for fixed z. Okay. Over lambda plus a, so and z is fixed, lambda is non-zero, and a is arbitrary. That's one family of orbits. Another family are lines. Z is 0 and y is non-zero. Right, yes. Lambda non-zero. And the rest are fixed points. Fixed points, so it's z equals 0, y equals 0. So let me draw the picture. Z, y, x. So where z is non-zero, we have all possible parabolas shifted and whatnot. And then with here we have lines where z is 0 and we have a line of fixed points. We have plinth ideal. Plinth ideal of D is, I hope it's Z. And so outside of Z equals 0, we can collect all those parabolas into one cylinder. But the question is, if I add those lines without the fixed points, would I still get a cylinder? Question. So is A3, well, my non-affine cylinder, right? Generalized cylinder. So is A3 without y equals z equals 0 a non-affine cylinder? That's the question, not because it's hard, but because I was too lazy to think about. I think it's pretty doable, and I think the answer is no. It might look hazardous because it seems like it's connected to some kind of cancellation problem, but I think in this particular case it's pretty doable. So if it's a cylinder, then it would be, I guess, isomorphic to something like this. A2 without the origin. Or you would have...
What is the question?
So we have a plinth ideal generated by Z. So outside of Z, it's a cylinder, right? So the question is, if I add something outside of plinth ideal, if I add those orbits, additional orbits, but not the fixed points, would I still get a cylinder, but not non-affine cylinder?
You mean just cylinder, what does it mean, non-affine cylinder?
Well, something like this. Such that alpha acts along those fibers.
So you need not geometrically this is a cylinder, but you need the
Yes, of course, yes.
alpha
Yes,
x
yes.
segmentation.
Of course, geometrically it's a cylinder, but it does not respect the action, right? We want it to respect the action. So that's the question. So
All principal cylinders are in the complement.
yes,
So
in the
and any cylinder is covered by principal cylinders.
I don't know.
Of course.
It's not clear. So I hope it's a counterexample. So maybe you will.
Wait. Any open substance is covered by a principal open substance.
Yes.
And if X is the cylinder, then okay.
And another question. Well, if the answer is yes, then the question is it true in general that if I just remove fixed points, I would get some non-affine cylinder in general, if it's not a counterexample. And another question is, okay, I'm starting to forget what I was planning to do here. And another question is, so if I take, so plinth ideal here is principal, so it's not interesting, but it may be not principal, and the question is, if I take the union of all the cylinders, would it be a possibly non-affine cylinder? So can two cylinders form a union which is not a cylinder? Okay, so is the non-zero locus of this plinth ideal a non-affine cylinder, possibly non-affine cylinder. Okay. And now to return to the main purpose of the talk. This was some brief stray from the main path. Now we return to the main path, and here let me finish the section with a definition and then start the next one with another definition. So X is a variety. Okay, two definitions. So here, let U be a cylinder. So U is a cylinder inside cylinder in X. And pi is the natural projection. So is the projection to Z. Okay, so a subset, just an arbitrary subset, a subset S in X is called invariant with respect to the cylinder if the formula holds. So the intersection of S with U is the pre-image of this intersection. So what does it mean? It basically means that we impose no restriction on S outside of cylinders. It can be whatever outside, but as soon as we have a point inside of the cylinder, we must contain the whole fiber. Together with the point, we must contain the corresponding fiber. And of course, one can easily see that this is just the same as invariant with respect to the induced action, an induced action. Right? So it induces an action, those fibers are orbits, and This definition exactly says that it's invariant with respect to this action. And just as a continuation of this definition, so if I have a family of cylinders, then a subset is called invariant, the same invariant with respect to this family, if it's invariant with respect to each one. If it's invariant with respect to all yours. Okay, so just basically the same notion of invariance for actions. Okay, and now we move to flexibility. Cylinders and flexibility. Flexibility. Okay. And just as I said, or maybe let me recall this in this way. I'll just say that, well, first of all, I want to define S out. So given a variety X, we define the group of special automorphisms of variety X to be just the subgroup generated by all GA actions on X. Inside of out X. And then I just don't want to go into details. I'll just say that X is flexible if this subgroup of special automorphisms acts on the regular locus transitively. Okay. So not to waste much time on this, I'll just say it in this way. And well, the definition does not depend on affine or not, but we will only consider flexibility of affine array. Okay, so the main purpose of this talk is to prove flexibility of two families of varieties. So, but before this, a little bit of preparation. So first of all, I want to, similarly to this geometric criterion of existence of a GA action, I can formulate a geometric criterion for flexibility as follows. So, yet another definition. So X is a variety, and calligraphic U is a family of cylinders. So UI, a family of cylinders in X. So this family is called transversal. U is transversal. This is definition due to Peripechko. U is transversal if what? If, let me say this like this. If no proper subset of everything that they cover, so of the union, is invariant with respect to this family. Is invariant with respect to this family. Okay. And immediately I can formulate a geometric criterion of flexibility. So X affine, its dimension is at least 1, just a technicality because there are no cylinders inside a point. And then X is flexible if and only if X, the regular locus of X is transversally covered by cylinders which are principal in X. Okay. Well, one direction is clear because if you have such a cover, you can consider all the induced action, and this exactly says that there are no invariant subset, no proper invariant subset, so that means the action is transitive on the regular locus. Well, the converse is a bit more trickier, but still not so hard. Actually, when I prove the converse, I use the theorem that this transitivity of S out implies infinite transitivity. So I use infinite transitivity. Okay, so that's flexibility of affine varieties, and in a similar fashion we can consider flexibility of affine cones over projective varieties as follows. So now we will actually shift towards projective geometry. I hope you're happy. So now we have the following setup. So X is a smooth projective. H is a very ample device. Okay, well, just very. H is very ample. And then I can consider the affine cone. So H defines an embedding X into some, well, that's redundant here, just smooth projective. H defines an embedding into some projective space, right? And then we can consider the affine cone with respect to H over X, right? Just take the affine space from which you obtain the Pn and take the same equations that define X here. You will obtain the affine cone. And before we formulate a similar theorem for affine cones, we need a notion of polarity. So definition, I think it's the last one in the stroke. So a subset, well, in these settings, a subset U, an open subset, okay, an open subset U is called H polar. If the complement is a divisor is a support of some divisor D such that D is linearly equivalent to dH for some natural H. Okay, so if you can find a divisor which supports the complement, and this divisor is linearly equivalent to some multiple of H, okay? And note, if the Picard number of X is 1, so if pic X is isomorphic to Z, then it just follows immediately from this definition that everything is H-polar. Well, then every open U of pure codimension 1, so that means the codimension is a cylinder of pure codimension 1, and in particular affine. In particular, if U is affine. So there's this theorem that if you have an affine open subset in a smooth variety, then the complement has pure codimension 1. Well, yes. So I need the complement here, such that X without U of pure codimension 1. So in this case, everything is automatically H-polar. So every this D cannot be principal divisor. You can always just take the union of prime divisors. It can never be principal because otherwise you would have on your complete variety a function which is regular, right? In particular, if U is affine, so every open is H-polar. Okay, and that's actually will be the case we're most interested in. Our variety X will be of Picard number 1. And the theorem by Перепечка, famous theorem. The year I think is 13. So if X is transversally covered by H-polar cylinders, then the affine cone is flexible. X is transversally covered by H-polar. So here we cover not an affine variety but a projective variety, and then we deduce flexibility of the affine cone. So X is transversally covered by H-polar cylinders. Then the affine cone is flexible.
Is it true other direction?
Is it? So I... Is it open? Really? It's just awkward to think about because how it works. You have a cylinders, you induce a cylinder on the cone, and then you get an action.
If you have homogeneous one, you can put it down.
Homogeneous with respect to the one-dimensional torus. Okay.
What is known, if the cone is rigid, then there are no cylinders.
Okay, if there are no actions, then there are no actions. But yes, it's hard to see whether an action here can be lifted to action here.
If you have an action on the phone, you can make homogeneous version of it
Yes.
and extend it to a symbol.
Yes. Okay. But
homogeneous
a lot of.
flexibility.
Yeah, okay.
Flexibility is not equal.
okay. I see. So you can always get an action, but it's unclear whether there are enough of them. Okay. I mean a cylinder. Okay, and that's all the preparation we need. Now we move to the 2 section where we discuss the results of the paper. So the section 3 is about quadrics, mainly complements of quadrics. Complements of quadrics. So first of all, let me recall. If you have a hypersurface in a projective space, X inside of projective space, a hypersurface, then actually the complement is affine. Well, an easy way to see this is through Veronese embedding, for example. Because the complement to a hypersurface after Veronese embedding becomes a complement to a hyperplane. So that's something affine, and actually Veronese embedding immediately gives you embedding of this stuff into some affine space. Okay, and we'll discuss those complements here. So what do we do? So let X in Pn n is at least 2 smooth quadric, and let me denote the complement by y. Okay, so an easy exercise here is that if I have a point x in x and I want to consider the projective tangent space, so I will denote by fat t x x the projective tangent space inside Pn. So if I have a point, then so basically you have a point, you can always consider some affine chart, right? So in this affine chart you have this embedding of the usual tangent space into affine space, okay? And you can just take the closure inside Pn after this. So just basically the same as in the affine space.
Projective subspace that touches.
Yes, that's the projective subspace. It touches it. Yes. So if I have a point, then there exist coordinates x0 and so on xn of Pn such that x is the point 0, 1, 0 and so on 0. The tangent space is given by the equation x0 equals 0. So x0, that's the 0 locus of x0. Well, that's easy, right? That's easily true, but what we have also, and x, that's a quadric, is given by this quadratic form, so x0, x1 plus g of the rest. So you can always plug 2 coordinates in this way. Okay, so why do we need this? It's because we can find a cylinder. So in those coordinates, it's easy to find a cylinder in the complement as follows. So, okay, so let us note the following. So if I take this complement and I remove this tangent space, what do I get? That's the principal open subset of y given by x0, right? On the other hand, y is the complement to the quadric given by this equation, so this is this thing. So it's principal open subset x0f, right? Okay, but then you remove a hyperplane, so you obtain an affine space. So you obtain a yes.
I don't understand. The first distinguished subset is this inside Y.
Yes.
So it is of coordination 1 in the space.
Y is the it's an open subset. So if you first, so here we first remove f, then x0, but if we first remove x0, you will get an affine space. So you have this thing. So you get d of affine space of f restricted to x0 equals 1, right? Remove a hyperplane from a projective space, get an affine space, okay? But this thing is finally the cylinder that we need. So I claim that this is isomorphic to A1 star, the punctured line without a point times A n minus 1. So it's not just a cylinder, it's a huge cylinder. We have a lot of fibers, and every dimension here gives me a new action, and they act like linearly independent. So why is that so? We have an isomorphism. Just explicitly we can write as follows. So here the coordinates x1 and so on xn. Here we map it to f of 1 x1 and so on xn, then x2 and so on xn. Okay. Yes, f is non-zero, so you get something like this, and the inverse is like this: t x2 xn maps to t minus g. G is this one of x2 xn, x2 and so on xn. So that's a cylinder.
I'm sorry, and the beginning of this
Here?
yes, why the complement to projective tangent space is this open subset.
As we proved, we can choose such coordinates. Just this is given by x0 equals 0. So the complement is given by x0 is not 0. Okay?
And why x is given by this equation?
Well, that's a claim. It's an easy exercise, but
Is it that x0 and x1 are symmetrically in this f? And
Yes.
I do not understand why in the tangent space they are not. Because x is this point. Okay.
yes, if you have this point, you get this tangent space. If you have this point, you get this
I'm
tangent
sorry.
space. So that's a cylinder, and we claim that lemma. So that's a transversal covering. So this set of complements to tangent spaces for all points is a transversal covering.
The transversal covering
y. So those are principal cylinders, and they transversally cover this affine variety. So in particular, we obtain that y is flexible. But we do not formulate yet this result because we want to prove something more general. And before this, a remark that actually it is quite easy to see that y is flexible because there is a semi-simple group actually. Transitively. So this is semi-simple, acts on y transitively, then automatically it follows that y is flexible. But then you may ask, then why in the world do we need all this stuff? Well, actually, we need this stuff to prove flexibility of complements of arbitrary quadrics, not just smooth quadrics. Yes.
It is not did you try to formulate it in terms of dual variety?
What do you mean by dual variety?
When you sandwich point to have a plane and all this.
Oh, no.
Maybe it can be.
I don't know. Well, the way we prove this is we actually take a finite collection of cylinders. So, two cases: the odd dimensional case x m y m, the odd dimensional case. Well, smooth quadric means actually that it's of full rank, right? So full rank quadratic form. So in odd dimensional case, it is enough to take those m cylinders corresponding to these points, and in even dimensional case, we take many more cylinders. So we take for each point here and plus one more. Okay.
And this part is true for any g if f is not a quadratic equation but any equation of this form, then you obtain this big cylinder.
Yes, one would love to think about this in that way, but it's a variety in a projective space. So if you have this equation, then this is homogeneous. Yes, it would be nice to have this, but it doesn't work like this. Well, actually, this idea was used in some other paper. I've seen it there. They used it to prove, to find cylinders in some cubics actually. So, yes, and the question is maybe one can generalize this construction and find cylinders in some other varieties. And now, how do we move from this to an arbitrary quadric? Well, I don't really, or do I have the time for this? So, okay, let me just draw some pictures. So, projective cones. It has nothing to do with affine cones, it's some really independent construction. So assume that you have some big Pn and you have two complementary subspaces. So think about this as complementary subspaces in the corresponding vector space, right? So they intersect trivially and they are large enough, as large as possible. So in projective terms, they intersect trivially, they do not intersect, and they are as large as possible. So this is some projective linear subspace K, and this is some projective linear subspace L. And suppose you have some projective variety here, x0. Then the projective cone is you just lift it to a bigger variety in the whole Pn by adding all the possible subspaces. So for each point, you take the subspace through this point and L, and you take all the union of all those subspaces. That's so x0 gives you another projective variety. So it's inside of K, it's inside of P.
It's drawing of x0 and the y.
Yes. So it's really simple construction, because what's actually happening? If I have here coordinates y0, yl, here coordinates, I mean in L, and here in K I have coordinates x0, xk, and this x0 is given by some equations, hm equals 0, then you just take those equations in the bigger projective space. And it is can be easily checked that what you get is this construction. Just from the subspace, take the same equation. You get this x0 hat. And so this is closed. When this is closed, and similarly I want to define for open. So if I have an open, inside of K,
You remove the line, you obtain a cylinder over x0, right?
no, we'll talk about this a bit later. So I want to have also a lift of some open. How do I do this? Well, I just take the complement, right, inside of U, lift it, and then take the complement, right? So what's happening here? This open, I also have every subspace like this, but then I remove this L. That's what I do. So how do I obtain U hat? I also take all those subspaces from each point of view, but also remove L. So that's how it looks. And the thing here is the following. So suppose U in K is open and contains a hyperplane. So let me draw another picture with just a point to make it easier. So here I have U open, and I want to have a hyperplane in the complement. So such that, so that's L, that's K, that's just all the lines. So here L is 0 dimensional. So suppose U in K is open and the complement contains a hyperplane. I mean the hyperplane inside of K contains a hyperplane. H given by H equals 0. Okay. And then if I have this additional condition that U has a hyperplane in the complement, then I have a cylinder. Then I have a cylinder. Then this U hat is a cylinder U times A L plus 1. Should I write the formula for the isomorphism? Okay. So how does it work? So here we have coordinates x's and y's. They map to two pairs of two tuples of coordinates. The first one is just the same axis, and the second one is y0 over h, and so on, yl over h. Yes, because when I have U hat, here I remove this hyperplane. When I take U hat, I remove the hyperplane in peak Pn through this H and this L. And conversely, when I have two tuples here, x0 and so on, xk and t0, tl, they map to x0 and so on, xk, h t0 and so on, h tl. So let me explain a bit. So what's the problem here? If you remove just the L, those lines here, they are affine lines, A1s, but they still have this attraction point. So they tend to one point, so that's some A1 bundle certainly, but they cannot yes, they cannot trivialize because they have some attraction point here. I'm not sure, but I just can't write an isomorphism for you. Okay. Okay, yes.
Then it should be like A1 times U.
Well, I don't know. It just doesn't work. if okay. So you can try to write some isomorphism formula, but it just doesn't work. So in my opinion, they just have some common attraction point. And when you remove some hyperplane together with this point, then they trivialize. Okay. U is, well, it doesn't matter. It can be affine, can be affine. Okay, so that's the projective cones, more or less. And why do we need them is just because if I have a quadric of rank n, if x and pn quadric of rank r, then x is a projective cone over a smooth quadric in p r minus 1, right? Is a projective cone x0 smooth inside smooth quadric in p r minus 1, okay? And I think you get the idea. So here we want a hyperplane. We have a hyperplane. We obtain a bigger cylinder, so with this AL plus 1 we can move along those lines. With the cylinders there we can move here. So overall, well, some exercise, I guess, it gives us flexibility. Yes, I hope so. So I tried to come up with some general argument that it works for arbitrary u as long as it contains a hyperplane. So yes, the argument is general, but we use this for the quadrics. So finally, let me write this in this way. So this.
Do you have some counterexamples that projective cone over a smooth variety, which can be corresponds to a flexible variety, so relatively by cylinders that this projective cone is not physically covered. Is it possible?
So you want to have
I have a
projective here, right? You take a cone, and then you want to.
You, as far as I understand, you have a rather general technique
Yes.
to deal with projective cone.
But with complements of projective cones. It's complements. So I take variety here, take cone, and then take the complement.
Okay.
The complement to a cone. Not
But
the.
there is a condition that there is such H.
Yes.
Do you have
A counterexample.
that, H does not exist and hence this doesn't work?
No, I don't have.
Okay.
Yes, that's maybe another question. Is it? Do we need this H? Do we need this H? That it's certainly here in the formulas, and you can't really do the formula without this H.
Yes, it is a problem.
It's a problem, yes. So this gives what? This gives a transversal covering of y, the complement for any quadric x of rank at least 3, right? At least 3. So theorem x inside Pn quadric of rank at least 3, y is the complement, then y is flexible. That's a smooth affine variety, mind you. Smooth affine variety.
What is wrong with rank 2?
Rank 2 quadric is just 2 hyperplanes. That's reducible.
So, if there is some this general construction, it is probably some proposition that we plug quadrics in.
Yes, yes.
So is there some proposition written down?
Yes, it's written down in the work that is to be published.
Yeah, but can you write it down? Because
Oh, write it down. Okay. Okay. You want this? Okay. Do I have the time? Okay, I have some time. That's fine. I can write down the proposition as follows. So, proposition. Or can I? Or can I? Yes. So, x0 in K projective variety. Y0 is the complement, right? Then X is the affine cone, or is the projective cone over X0. U calligraphic is a family of cylinders. So transversal covering of U0 by a principle, oh, it doesn't matter, just by cylinders.
we use in terms of flexibility. Can it be formulated in terms of flexibility like in this flexible or that flexible?
No, because we need this additional condition for H, right?
Okay.
Yes, yes.
So this is some special.
So transversal covering of Y0 by cylinders such that the complement contains a hyperplane, has hyperplane for all I, and that's it, right? Then this new family, U calligraphic hat of all those UI hats, is a transversal covering, right, of the complement. Is transversal covering of Y, which is Pn without X.
How does this relate with flexibility?
Well, you get a transversal covering of bicellulars.
By principles?
If those were principal, then those are still principal.
Okay.
Okay, so that's how we obtain this theorem. Okay. And the last part of my talk, so that's one family of flexible varieties that we obtain, and the other family is, I have 10 or so minutes. The last section is smooth, complete intersection of two quadrics. So what's happening here? So x equals q1 cap intersection with q2. That's this. SCI of two quadrics. Well, a Pn plus 2 and at least 3. Okay, so that's the dimension of x is n. And here the remark, what's going on with 4 small dimensions. So if n equals 2, then this is x is a del Pezzo surface, right? Del Pezzo surface of degree, of course, 4, intersection of two quadrics, and flexibility of affine cones or del Pezzo surface of degree 4 is proved in famous Peripetchiko's paper. The paper with the yes.
Degree 4.
Yes.
Yeah,
For some cones, for some affine cones, yes. And if n is 1, then there is no flexibility because x would be just an elliptic curve. X is elliptic curve. And another remark, coordinate-wise, how does it look? There exist coordinates such that Q1 and Q2, so they both can be diagonalized, given by the first one is just the sum of squares, the usual sum of squares, and the second one is the sum of squares with some coefficients. Where lambda i's are pairwise distinct. Okay. So that's what it means to be a complete smooth intersection of two quadrics in coordinates. Okay. Let me just briefly explain how do we prove that. Oh, first of all, x is a Fano variety of index index is the okay, I have index n minus 1 and Picard number 1. So what is index? Index is so in this Picard group you have your anti-canonical divisor or canonical divisor, and that's the index is the how do I say this? Well, you have your z, and n minus 1 is the your canonical divisor. So the number of times you have to add the generator of the Picard group to get your canonical. The subgroup generated, yes. The subgroup generated, yes, of course. Okay, so how do we, and it's of Picard number 1, so as we talked about this before, everything here is H-polar for every very ample H. So all we have to do is just to cover this X by cylinders transversally, so we don't need to worry about this polarity condition. Okay, and how do we do this? Okay, 5 minutes, just briefly an idea. So L, if you have a line L in X, just a projective line, linear subspace in Pn, it gives you a divisor dl, a prime divisor.
We prove the theorem that any such intersection is flexible.
Affine cone over any such intersection is flexible, yes. So prime divisor, any affine cones, it doesn't matter because it has Picard number 1. Prime divisor swept out by lines meeting L. Lines, of course, in X. So you have a line L, and you have all the possible lines that intersect this. So that was L, that's your DL. And then you have what? Then you have projection. You have a projection from this line, projection from L, a birational map to Pn. In fact, it is birational. You can resolve the indeterminacy of this birational map to obtain some Hironaka triangle, or in other words, you just need to blow up L. So sigma is the blow up of L, some X and tilde, and here you need to blow down the exceptional divisor. And that's your psi. And then what? That's also from another paper by Chiltsov, Kishimoto, Prokhorov, and Zeidenberg, I guess. That's this construction. So what it gives you is that psi actually gives you an isomorphism of X without this divisor with Pn without phi of E. No, yes, it blows down the proper transform, not this thing, but the proper transform of dl. Yes, it blows down. Yes. No. Yes. Yes, it blows down this dl. Okay. And this thing is a quadric. So that's how you get a complement to a quadric. So sum up, given a line, you obtain an open subset in X, which is isomorphic to a complement to a quadric, complement of a quadric. right? So summing up, sum up, L inside of X line gives you U inside of X open. U is isomorphic to Pn without a quadric. And what we do is we prove that there are enough of these divisors. So those U cover X. So proposition, these U's cover X. So you have covered some variety by another varieties which can be covered transversally by cylinders. An easy exercise shows that then if you take the union of all the coverings, you obtain a covering of X, a transversal covering of X. So theorem, then affine cones over X are flexible, and once again in coordinates, variety, affine variety. So let me just rewrite this. Xn squared equals 0, x lambda 1 x1 squared plus so on plus lambda n xn squared equals 0. In an, those are distinct, pairwise distinct. In an, for n at least 7 is flexible. No, fix is flexible.
So essentially, the complement to the quadric is flexible. So
Yes.
you cover
Yes.
variety with flexible flexible effect of the sum.
Yes, yes.
This sometimes it's better than just.
Yes, of course it's better because they have inside a lot of cylinders. And also a note.
Why n is bigger than 6?
So we had P n plus.
Plus one,
Okay.
then
Yes,
you
yes.
apply.
And note, this thing here is normal. It's normal. It's normal. It's a general fact that if you have a complete intersection, normal complete intersection of two projective varieties, then affine cones over this intersection are normal. And that's it, I guess. So thank you very much for your attention. I hope at least something was understandable.
Any questions? I didn't catch it all. The last part, how do we use that we have intersection of two quadrics?
That's the geometry, that's some geometry happening here. So that's some Fano varieties geometry. So that's some black box.
Okay,
Black box.
For one varieties of square number 1, there is a lot of cases when we have such a variational map, such a direction.
Okay, another question. I didn't catch any two quadrics which are in complete intersection. They are such diagonalizable in the same.
Yeah, it is it's a proposition in PhD thesis of Miles Rate. His yes, so if you have a variety which is a smooth complete intersection of two quadrics, then you have coordinates such that those quadrics are given by those
Okay.
equations.
And when you consider that just such a variety, affine variety, isn't it? Can you just explicitly give lots of these?
I can no.
So it's not obvious.
I don't know. Maybe it is. I don't know.
There are some bad computations. So probably you can't use them, but you have to get some.
Okay.
Nice formula.
My question is just maybe there are some trivial.
Maybe I don't know. So as I told in the beginning, there are people who don't like, who like geometry in algebraic geometry, right? I'm not this kind of people. I just can't do algebra in algebraic geometry, so I don't know any of these.
Okay. I do not like geometry. I like algebra, but I liked your talk much.
Okay, thank you.
It was rather clear and interesting. Okay, any other questions? Okay, then, thank you very much. And we have next
Oh, it was
seminar in a week. I don't remember what for.
Блин, понятно.